Hello and welcome to this FMSP online revision session. This session is looking at the MEI Further Pure 2 specification, and we'll be looking at three sections of the specification which are usually assessed all in question 1: calculus, polar coordinates and series. We'll look at calculus first, and the techniques listed explicitly here will be needed in questions on polar coordinates and series as well. You need to know about inverse trig functions. You need to be able to differentiate them. These results are in the formula books and it's worth remembering that, but you may be asked to derive them as well. You need to be able to recognise integrals in this form and use the standard results in the formula book to integrate them. You may also need to use trig substitutions, and the difference between this and the A2 core questions is that in Further Pure 2 you won't be given the substitution, you'll have to work it out for yourself. You'll also need to know the trig identities from your A2 core and use those to integrate functions. Key points for calculus questions. Have the formula book open at the page with all the integrals and derivatives. There are no marks for misremembering something that's in the formula book. Make sure you know the product rule, quotient rule and chain rule, and that you're confident with integrating by substitution, parts and partial fractions. This is just Core 3 and Core 4 work with some extra functions. The questions may be a little bit harder, and you will have to choose your own substitutions, but preparing for this part of the Further Pure 2 paper will help you with your preparation for Core 3 and Core 4 as well. For polar coordinates, you need to be able to convert between polar and Cartesian coordinates. You need to be able to sketch curves with simple polar equations, but note that you're allowed to have a graphical calculator in the exam, so I strongly recommend that you beg, borrow or buy one and learn how to use it. You'll probably want to use your tried and tested scientific one for some parts of the exam, but it's okay, you'll be able to take both in. And also for polar coordinates, you need to find the area enclosed by a polar curve, but this formula is in the book, so really that's just another bit of calculus. When you're doing your curve sketch, use a graphical calculator to check the basic shape. If there's a parameter that means you can't just plug the formula in, then choose a value for it. Avoid 0 and 1 so that you don't find that 1 squared is 1 and doesn't really make any difference to your curve or whatever it might be doing. Do check the intersections carefully and make sure you think about those in terms of any parameter rather than in terms of the value you've just chosen. And do take care with the limits of your integral. Often they'll be given, but not always. Remember that if r is positive, your curve should have a continuous line, and if r is negative, it should have a broken line. This won't show up on your graphical calculator, so you'll need to remember that. For series, you need to be able to find the Maclaurin series of a function and the general term. They won't give you anything too difficult there. There are several Maclaurin series standard results in the formula book, and those say for what values of x they converge. You may need to adapt one of the given series, and you may then need to adapt the restricted set of values. The key with this is making sure that it's all set out really clearly. You don't need to draw a formal table with pencil and ruler, but it does help if you lay everything out in a tabular way. Set the derivatives down the left-hand side of the page and their corresponding values on the right. Take great care when you're making the substitution, and leave the simplifying until the next line of working. Don't try and skip stages, it's not worth it. Find the correct number of terms asked for in the question as well. You may lose marks, you'll certainly end up doing more than you need to if you're not careful. And make sure you're on top of all that calculus work from the A2 core. Remember that you can differentiate or integrate a power series term by term, and that all the formulae that you will need are given, so just copy carefully. All three topics in this section have very little to memorise, but they do need lots of practice, so let's look at some exam questions. It's a good idea to read through the whole question first, and unfortunately looking at this one you see that it's not an easy start to the paper. 6 marks for the first question. However, it does tell you pretty much how to start, and there's a hence show that with an answer, so at least you'll be able to check you've done it right. For part 2 we've got a show that, so we need to make sure you've got plenty of clear working, at least 4 marks worth, and notice that you're given the final answer, so there won't be any marks for that, the marks will all be for the working. Part 2 is a little bit non-standard, so we'll have a look at that one when we get to it. For part 3, where it says sketch the curve, do make sure that you include all the features that you've already found out about in other parts of the question. So for example, these greatest and least positive values of r should feature in your sketch. Okay, let's start part A. You're given that y equals arctan root x, and you've got to find dy by dx. Well, differentiating arctan is not particularly nice. It's much easier to differentiate tan. So that's an x, not a 2. Let's rewrite that and say root x is tan y. I could differentiate implicitly here, but I think it's probably easier to square and say x equals tan squared y and find dx by dy rather than dy by dx. Use the chain rule, that's 2 tan y, and differentiate tan, you get sec squared. That results in the book. Turn that upside down, dy by dx is therefore 1 over 2 tan y sec squared y. However, I need that in terms of x, not in terms of y, so I need to substitute back. Tan y is easy, that's root x. For sec squared, I'm going to need to use an identity. There's one relating tan and sec. You may have memorised all of these, but they're quite easy to work out in the exam if you prefer to do it that way. Sine squared plus cos squared is 1, it's the one that everybody remembers. And if you divide through by cos, you'll get tan squared plus 1 is 1 over cos, which is sec squared. So sec squared is tan squared plus 1. So we'll write that in, tan squared y plus 1. And tan squared is equal to x, so that gives me 1 over 2 root x, x plus 1. So I've done that, I found dy by dx, given my answer in terms of x. Now I need to do the integral from 0 to 1 of 1 over root x, x plus 1. Well, that's exactly double what I ended up with as my derivative, so I need double what I started with, so that must be 2 arctan root x from 0 to 1. So 2 arctan 1 minus 2 arctan 0. Arctan of 1 is pi over 4, arctan of 0 is 0, and that gives me pi over 2, which was the given answer. For part B, converting from Cartesian to polar coordinates, I need 3 key results. X is equal to r cos theta, y is equal to r sin theta, and x squared plus y squared is equal to r squared. So if I start with x squared plus y squared equals xy plus 1, x squared plus y squared is r squared, xy is r cos theta, r sin theta, so that's r squared sin theta cos theta plus 1. Now, comparing with what I'm aiming for, sin 2 theta, you'll remember, is 2 sin theta cos theta. There are lots of 2's in that, so I'm going to multiply through by 2. That'll save me having to use any fractions. Now I can convert that 2 sin theta cos theta into sin 2 theta. I need r squared on its own, so let's get the r squareds on one side. Take out a factor of r squared and divide by 2 minus sin 2 theta. And there we are. So the greatest and least possible values of r. Well, r squared is a fraction, so the maximum value of r squared will be when the denominator is minimal. I want to make that as small as possible. Denominator minimal. So the minimum value of that denominator is going to be when sine 2 theta is at its maximum value of 1. So maximum value of r squared is 2 over 2 minus 1, which is 2. So the maximum value of r is root 2, and that is going to be the case when sine 2 theta equals 1, which means that 2 theta is pi over 2 or 5 pi over 2, and theta is therefore pi over 4 or 5 pi over 4. Similarly, the minimum value of r squared will have the denominator maximal. And that means that sine 2 theta will be minus 1. So the minimum value of r squared is going to be 2 over 2 take away minus 1, which is 2/3, and therefore the minimum value of r is going to be root 2/3. This is going to be the case when sine 2 theta is minus 1. In other words, 2 theta is 3 pi over 2 or 7 pi over 2, so that theta is 3 pi over 4 or 7 pi over 4. Now we need to sketch the curve, and we need to use what we've done before. The maximum values of r are when theta is pi over 4 or 5 pi over 4, so it'll lie on there, and the minimum values will be on that axis there. So what we have is an ellipse with its major axis on that diagonal line x equals y. So just note max values of r when theta is pi over 4 or 5 pi over 4. Min values when theta is 3 pi over 4 or 7 pi over 4. Okay, let's see how this question is marked. So for part A, there is a method mark and an accuracy mark for rearranging and differentiating. You could use the chain rule or implicit differentiation instead, and an accuracy mark for ending up with an expression for dy by dx in terms of x that is correct. For the second part of the question, there is a method mark for having something times arctan root x, and an accuracy mark for that something being 2. And then there's another accuracy mark for completing that working to the given answer of pi over 2. For part B, there is a method mark for using one of these identities. There's then an accuracy mark for getting this bit right and for getting this bit right. And then one final accuracy mark for completing your solution correctly without any mistakes down to the given answer. For part B, there is an answer mark B1 for identifying the maximum value as root 2. There's a method mark for attempting to solve this equation here, and an accuracy mark for getting both those angles. You'll get A0 if you put any extra ones in that shouldn't be there within the range. They will probably ignore extra values which are outside the range. And similarly for the minimum value, there's a mark for identifying the minimum value, a mark for attempting to solve this equation, and an accuracy mark for getting both the angles. And finally, for sketching the curve, there is one mark for having a closed curve, roughly elliptical, and no points or dents. There's another mark for having the major axis of the ellipse along that line x equals y. Okay, there's quite a bit of material to cover, so we need to look at another question to cover some more areas. We've got another polar equation needing sketching, but this time we've got to find the area of the region enclosed by the curve, noting those limits of 0 to 2 pi. Note that sketching the curve is not going to be too difficult, but that finding the area might be quite long. It's worth 7 marks. Note that all of these need to be done in exact form, so no decimals. And look how similar these two are, and yet the second one is worth twice as many marks. Okay, doing our sketch. It's useful to draw a table of some values. If theta is 0, r is a. If theta is pi over 4, a is 1 minus 1 over root 2. If theta is pi over 2, r is 0. 3 pi over 4, pi is a. A 1 plus 1 over root 2. If theta is pi, then we just get a. So that means what I've done so far is I've got from a to 0, and then out again to minus a. So it's going to go down, and if you're familiar with these, you'll know it's going to be a cardioid. So in fact, all I need is to know what that bottom point is. And if theta is 3 pi over 2, then that bottom point is 2a. So I need to finish my curve like that, 2a. Choose a value, perhaps a equals 3, to plot that on your graphical calculator and check. Finding the area enclosed by the curve, we've got r equals a 1 minus sine theta. Copying carefully from the formula book, we know that the area is from 0 to 2 pi, that was given, a half r squared d theta. That's equal to a half a squared 1 minus sine theta all squared. Expand that bracket. 1 minus 2 sine theta plus sine squared theta. Now I can't integrate sine squared theta, so I'm going to use an identity. You may have remembered all of the identities, but if you choose to just remember some of them and work them out, this is a good strategy. This is the one I always remember. Cos 2 theta is cos squared minus sine squared. Cos squared is 1 minus sine squared, so that gives me 1 minus 2 sine squared theta, and therefore sine squared theta is equal to a half 1 minus cos 2 theta. Working them out like that means I don't have to remember which ones the minus signs come into. Okay, let's substitute that in. 1 minus 2 sine theta plus a half 1 minus cos 2 theta. And now I can integrate. Half a squared integral. Integrate 1, I get theta. Integrate minus 2 sine theta, and I get plus 2 cos theta. Integrate a half, and I get theta over 2. And integrate a half minus a half cos 2 theta, and I get minus a quarter sine 2 theta. From 0 to 2 pi. So theta and theta over 2 will give me 3 pi. Cos of 2 pi is 1, so that will give me 2. Sine of 2 pi is 0. Take away theta is 0. Cos of 0 is 1, so that's plus 2. And sine of 0 is 0. So the 2's cancel out, and I'm left with 3 a squared pi all over 2. Now my 2 straight integrals. Have a look in the formula book. I've got an integral of a function like this, 1 over a squared plus x squared. There's nothing in front of the x, so that means that I need to rearrange that to get rid of the 4. So I'm going from minus a half to a half, 1 over 1 plus 4x squared. So if I take out a factor of a quarter, that's dividing the bottom of my fraction by 4, and that gives me a quarter plus x squared, which is now in the correct form. I've got a squared is a quarter, and that means that a is 2, and 1 over a is a half. So, using the formula in the formula book, that's just 2 arctan 2x, from minus a half to a half. That's a half arctan 1 minus arctan minus 1. Arctan of 1 is pi over 4, and arctan of minus 1 is minus pi over 4. So half of pi over 4 plus pi over 4 is pi over 4. So that was really just about substituting into a formula in the formula book. Part 2 is indeed harder. Looking through the formula book, there's nothing that looks like that. So I'm going to need to do a substitution. And if you've got 1 plus something x squared, what you want there is 1 plus tan squared, so that you can replace that with sec squared. That means that my substitution needs to be 4x squared is equal to tan squared theta. And that means that x is equal to a half tan theta. And that's the substitution I want to use. Having done that, it's just like your core work. Differentiate that and I get a half sec squared theta. That's in the book, you don't need to remember that. X is minus a half, implies that tan theta is minus 1, and therefore that theta is minus a quarter. And if x is plus a half, then tan theta is 1 and theta is pi over 4. I've now got all the information that I need. So the integral from minus a half to a half of 1 over 1 plus 4x squared to the 3 over 2 dx is, change my limits, so I'm going from theta is minus pi over 4 to pi over 4, 1 over 1 plus tan squared, which is what I wanted, to the 3 over 2, multiplied by a half sec squared theta d theta. Right, now I know that I'm doing my limits and everything in terms of theta. I don't need to put the thetas in on the limits anymore. And I've got sec squared theta over 2, 1 plus tan squared is sec squared theta to the 3 over 2. So that's sec squared over, sec squared to the 3 over 2 is sec cubed. And that simplifies to 1 over sec, which of course is cos. So I've got a half cos theta d theta, which of course is dead easy to integrate. It's just a half sine theta from minus pi over 4 to pi over 4. That's a half 1 over root 2 minus 1 over root 2, which is 1 over root 2. Okay, let's go and have a look and see how the mark scheme works for this question. For part A, there is one graph mark for correct general shape, including symmetry in the vertical axis. And the second mark, which is dependent on the first one being correct, is correct form at the origin and no extra bits. Note that if you have a point at the bottom but it's otherwise correct, you would get G1, G0. For part 2, finding that area, there is a method mark for an integral involving 1 minus sine all squared. There's then a method mark for its expanding and an accuracy mark for getting that all correct, including the limits up to that point. There's then a method mark for using an appropriate identity, and 2 accuracy marks for correct integration. You'd get A1 if there was 1 error. And a final accuracy mark dependent on the previous working if you've got through to the end and got it right. For part B, that first integral, there's a method mark for spotting that the integral is arctan, or for using any tan substitution, which would be an alternative method. There's then an accuracy mark for having the quarter times 2 at the front and 2x, so having the detail correct. And then another accuracy mark for evaluating that correctly. For part 2, there is a method mark for any tan substitution. So if you spotted that you need something to do with tan, you'll get your method mark. There's then an accuracy mark for having that half sec squared there, and an accuracy mark for getting this far with your substitution and getting sec squared theta to the 3 over 2 at the bottom. There's then a method mark for doing an integration from a point of having something cos something theta, and an accuracy mark with follow through for if you had something of that form, getting a consistent answer. And then there's a final accuracy mark for actually getting the right answer. Now, neither of those two questions had anything on Maclaurin series, so we're going to do part of another question to make sure that we've covered everything. So I've got f of x is arctan a half x, I've got to find f dashed of x. I've then got to expand f dashed in ascending powers as far as x to the 4. And then hence, and it's important that I do it hence by using the previous expansion, integrating to get f of x up to the power x to the 5. Remember, layout is the key for these. So there's f of x, and look in the formula book and use the chain rule. We get that f dashed of x is equal to a half times 1 over 1 plus a half x all squared. So that's 1 over 2 1 plus x squared over 4. Okay, so f dashed of x was a half 1 plus a quarter x squared to the minus 1. Writing it in that form because I'm going to need to expand using the binomial. So that's a half 1 minus a quarter x squared plus 2 over 2 factorial a quarter x squared squared minus dot dot dot, which comes out to be a half minus 1/8 x squared plus 1/32 x to the 4th minus dot dot dot. So to obtain an expression for f, I simply need to integrate that, which gives me a half x minus 1/8 x squared, 1/24 x cubed, plus 1/160th x to the 5 minus dot dot dot, and don't forget your constant on the end. However, f of 0 is arctan of 0, which is 0, and that means that my constant must be 0, which gives me a final result. F of x is a half x minus 1 over 24 x cubed plus 1 over 160 x to the 5 dot dot dot. Well, that's all you need to know for these topics. I look forward to your company in the rest of the FP2 videos and wish you all the best for the exam. Goodbye.